Let's continue our discussion about nuclear power plants, fission-based power plants. One of the biggest concerns about nuclear power plants is their safety, and that is what happens if an earthquake strikes or another sort of natural disaster or even a terrorist attack, what's going to happen to it? And indeed, serious consequences can happen, and it has happened before, especially with the recent Fukushima power plant's failure following the tsunami in Japan in the year 2011. So let's take a look at some famous accidents and what are the consequences. The International Atomic Agency, International Atomic Agency has designated a level, a scale of 1 to 7 that describes the severity of nuclear power plant accidents. It's called INES levels, International Nuclear Energy Safety levels. Level 7 being the most severe of all accidents. Now, we know that in order to maintain safety operation of nuclear power plants, we want effective K to be equal to 1. And for whatever reason, if K is greater than 1, then that's going to cause an overheat of the core. And the overheat of the core could cause the core to melt down. And then if it melts down, then the radioactive materials can leak out of the power plant into the environment, and that can cause long-term pollution consequences. And even if K is not exactly greater than 1, the heat that's generated by the nuclear reaction at the core needs to be transported out. Otherwise, the core temperature will still go up. Even after the nuclear reaction has stopped, the heat residual heat that's in there can still heat up the core, and that can still cause a meltdown. That's in fact what happened in the most recent Fukushima accident. Let's see here. There are many accidents, big and small, associated with nuclear power plants, and here are some more famous ones. This one in 1979 is perhaps the most famous nuclear accident that took place on US soil. And it's a level 5 accident. It happened in the year 1979. The place is called 3 Miles Island. It's in Pennsylvania. And what happened was a procedural error and poor safety training, which led to a partial core meltdown. Fortunately, this meltdown did not cause any huge catastrophe. The pollution, the radioactive pollution that leaked outside was minuscule, and it turned out that if you lived near that place after the accident, the radiation that you will be exposed to will still be less than the amount that you will get by eating a banana every day for a year. So it is, well, fortunately, it did not lead to any huge catastrophe, and there were no fatalities associated with that. But the year 1989, 10 years after that, on April 26, things were not that lucky. This was the date of the infamous Chernobyl accident. Chernobyl, USSR, is located outside the major city of Kiev in today's Ukraine. During that accident, there was an explosion due to the huge rise in temperature of the core, and there was an explosion which just blew off the roof of the entire power plant, and then a radioactive fire then raged, and radioactive smoke then escaped from that opening on the roof, and then radioactive cloud escaped through that and blanketed pretty much the entire Europe and much of the USSR at the time. That was the biggest nuclear power plant disaster in human history, and it caused a direct 50 fatalities directly linked to it. Those are mostly the workers who had to go in and to clean things up. 50 people died, and it also caused many cancer causes of cancer. There was a 10-fold rise in thyroid cancer detected in children near the site, and it also caused 300,000 people to evacuate. So that was a huge disaster. Even today, we're talking about more than 20 years after the accident. Even today, even with all this time going by, and even with a concrete casing that covered the accident site, if you stood near that site for 1 hour, you would get enough radiation that you would normally get everywhere else for about a whole year. So even today, it remains radioactive. The town is still a ghost town. Nobody lives there. Now, this is the newest accident. It happened on April the 11th to April the 20th of 2011, the Fukushima nuclear power plant. What happened was on this day of April 11th, 2011, there was a tsunami, and the tsunami caused by the earthquake damaged the power plant. The earthquake itself caused the foundation of the nuclear power plant to shake with an acceleration which is about 0.56 g, g being the acceleration gravity, and that exceeded the design capability of the nuclear power plant to withstand withstand the earthquake, which is about 0.4 something g. So, as a result, what happened was that the nuclear power plants, three of the reactors, their power grid, their power supply got cut off from the main power grid, and as a result, it cannot cool down itself. The cooling mechanism basically failed, and as a result, the core temperature went up, and it even caused hydrogen explosion, which made it difficult for people to come in and repair it, and so lasted a few days. So eventually there was a full meltdown in reactors 1, 2, and 3. Those are the three that were active right before the accident. Fortunately, the other three were offline. And even though it's being contained right now, it has caused a containment area which is 50 kilometers in radius. By U.S. standards, everybody within this radius should have been relocated. And the total amount of radiation released is about 1/10 of that Chernobyl. That was initially designated as a level 4. Now it is upgraded to a level 7 major disaster. Here are some numbers that tells us how much radiation has leaked out. The iodine-131, which is one byproduct of the nuclear power, and cesium-137 is another one. These are two typical ones. The iodine-131 radiation that leaked out of the power plant had a activity of 1.3 times 10 to the 17 becquerel. That is 1.3 times 10 to the 17 radiations per second. And cesium-137 has an activity of 1.1 times 10 to the 16 radiations per second. Now, iodine-131 has a half-life of about 8 days, so it is relatively okay. I mean, after a month or so, you don't detect that much. But the cesium-137, another byproduct of the radioactive waste, that is more dangerous because it's got a half-life of 30 years, so it's a long-term issue. And even today, the situation, even though it's under control, the decontamination process is far from over. It will take decades to do. And this Fukushima nuclear power plant is actually pretty close to one of the most populous areas of the world, which is the Tokyo metropolis area. So the environmental consequence is just unbelievable. And the Japanese government at one point banned any agricultural and fish products, seafood products, from within a certain radius of the power plant. And despite the fact that some of the radioactive elements, some of the radioactive fuel may have breached the concrete foundation and leaked into the ocean, it is believed that this is perhaps not going to pollute the world's ocean that much, because there is very strong current, fortunately, ocean current near that area, which would have taken this radioactive material and diluted to the entire Pacific Ocean. And when that happens, the radioactivity would shrink to an amount that won't really cause any damage to marine life. But in the coastal areas near Fukushima, the radiation could persist for a long time. Okay, now you can compare this amount of radiation with some reference. You know, 1 curie is defined to be 3.7 times 10 to the 8 disintegrations per second, and that is roughly the radiation activity of 1 gram of radium that was discovered by the Curies. But we have a lot more. Okay, so this is like the activity of 300 to 3,000 kilograms of radium that's leaked into the environment. So this is really a huge disaster. The environmental consequence of this disaster has not been fully assessed. We will not know it for decades to come. So before we talk about nuclear fusion, let's switch orders a little bit from the textbook. Let's discuss what kind of radiation damage all these fission products can do to living organisms, especially humans. When it comes to radiation damage, there are many units, and this is very confusing. So I have a list of some units that we frequently use, and I'll explain to you what they mean. Radiation damage to living organisms, to the tissues of living organisms, is primarily by the so-called ionization radiation. And that is, you have an alpha particle, beta particle, gamma, or some other particles such as neutrons. They carry a lot of energy. We're talking about MeV, okay, million electron volts. They carry a huge amount of kinetic energy, and this can cause, as they stream through the body, they can cause the molecules and atoms to lose electrons. They can literally knock the electrons out. So basically, you can ionize the atoms and the molecules, and then basically you can turn these into ions. Ions can then combine with other ions, and they can capture electrons and whatever. So basically, you can damage molecular and atomic structures. Okay, if you damage the structures of a lot of molecules, you can cause a cell to die. And then not only can you cause a cell to die, you can also alter the properties of the cell, which can turn it cancerous. So ionization radiation is what's really damaging to living organisms. Now, when it comes to units, we have to be careful. There are 3 layers that we have to talk about when it comes to units associated with radiation damage. The first layer is really just physical. That is, how much radiation has been emitted. Okay, and the primary units we use there are either becquerel or curie. 1 becquerel is defined as one disintegration event per second, as we know. And curie, as you know, is 3.7 times 10 to the 10 becquerel. It's 37 billion radiations or disintegrations per second. So these are just how much radiation has taken place. But how much radiation does a living organism receive or absorb? That is the second layer. Okay, so that's the second layer. How much do we absorb? Now, it makes a difference whether you receive something very energetic or something less energetic. Okay, so it's not a matter of how many particles you catch, but rather how much energy of these particles that you catch, or more precisely, the concentration of the energy, that is, per kilogram of body mass. How much radiation energy do you absorb? That is how we describe the amount of radiation that's received by the body. And to that effect, we define several units. The Röntgen was the original unit, which we rarely use, so I'm not going to even bother to define it. Rad is what we use still quite often. It's got radiation absorbed dose. So here we're talking about not just how much is emitted, but how much do we absorb. And as we discussed earlier, it is measured in terms of the energy of radiation that's intercepted by the body per kilogram weight or mass of the body. 1 rad is defined as 0.01 joule per gram. And that is, if somebody receives 1 rad radiation, what that means is that 1 kilogram of the body mass has received an energy from radiation in the amount of 0.01 joules. Okay, rad is not a prime SI unit. The prime SI unit for that is gray. It's called gray, G-R-A-Y, and its shorthand is G-Y. 1 gray is defined to be 1 joule of radiation energy received per kilogram of body mass. And so there's a conversion. Easily you can do a conversion here. 1 gray is equal to 100 rad. Now, rad is a large unit. We typically use millirad and microrad and so on. So again, that is how much energy of radiation a body receives per kilogram. But when you receive that radiation energy, how much damage does it do? That not only depends on this amount, how many rad, it also depends on what kind of radiation. It's alpha particle, beta particle, gamma particle, and so on. For example, photons carried by X-rays and gamma rays, they, relatively speaking, they do the least damage because they are not charged themselves, and they often stream through the body without actually interacting with the body, even though some of them do. So they have relatively a smaller amount of damage. On the other hand, heavier ions, heavier particles such as neutrons and alpha particles, they do a lot of damage. So even for the same amount of rad, alpha particle neutrons do a lot more damage than X-rays and gamma rays. So therefore, to assess the actual amount of damage the body receives from a certain amount of dosage in radiation, we have to multiply the rad by a factor, and that is called RBE, relative biological effectiveness. Okay, we use photons as a reference of 1.0. So X-rays and gamma rays have an RBE value of 1.0. And relative to that, neutrons and alpha particles are far more dangerous. Alpha particles, for example, has an RBE value of between 10 and 20, depending on the energy of the alpha particle. So they can cause 10 to 20 times as much damage for the same energy as X-rays photons or gamma ray photons. And neutrons are really, really bad too. So we have to take that dosage that you calculate, multiply by RBE. That actually gives you a number which will more or less represent how much damage this radiation can actually do to us. And that will lead us to another unit called REM, radiation equivalent in man. Whether the radiation that you receive is from alpha, beta, gamma, or whatever, you may get different RBE values and different rads, but if you get the same REM value, that means it does the same amount of damage, roughly speaking. Okay, so dose in REM equals dose in rad, which is how much energy that you receive per kilogram, multiplied by the effectiveness factor. Okay, so 1 rad of radiation exposed to gamma ray and 1 rad radiation exposed to alpha particles, they have the same dose in rad, but the REM value is very different. For alpha, you're looking at 10 to 20 times the amount in REM than the same dose that you got from gamma, because it's more dangerous. Okay, now this number is something we should really pay the most attention to, because this is, after all, a measurement, a numerical measurement of how much damage we have received from radiation. Again, REM is not a prime SI unit because it's given in rad. Okay, now we want an SI unit given not in rad but in gray. So there's a conversion here. I want to tell you both because both are still used quite often in literature. So when you read these things, you will come across both of these, rad and gray, but REM again is associated with rad, and if you convert rad to gray, this side also has a conversion. The correct unit corresponding to 1 gray times RBE is called 1 sievert. Sievert was actually the name of a doctor who studied radioactive damage to the human body. So 1 sievert is 100 rem, because 1 gray is 100 rad. You get that? Okay, so you replace this with 1 gray, you get 100 rem, which is 1 sievert. Okay, so what is 1 sievert dose of radiation? What exactly does it mean? It means that if you take X-ray or gamma ray, okay, and irradiate that X-ray gamma ray to a living organism with a mass of 1 kilogram, then if the intensity of the radiation is such that you give 1 joule of radiation energy to every kilogram of that body, okay, then how much damage does it do? Well, the damage is measured in 1 sievert. It's called 1 sievert because the RBE value for X-ray and gamma is 1, so this number is 1. Okay, 1 sievert is a huge number for radiation. It can cause extensive damage. So therefore, we typically do not use 1 sievert, we use millisievert, microsievert, and so on. Okay, how do these numbers how do these units work in real life? How bad is one sievert? How bad is one RAM, and so on? Well, let's see here. The, it turns out the background radiation that everybody receives just by walking around, just by exposing ourselves to the air, to the water, is about 0.1 RAM per year. Now, 1 RAM is 0.01 sievert. Okay, so 0.1 RAM is 1 millisievert, which is 0.001 sievert, so 1 millisievert per year. These are equivalent. Okay, that's a good thing to know. This only from background radiation. Now, we also get radiation from food, stuff we eat. A lot of things that we eat has a little bit of radioactivity in it, and we're not bothered by that because our body doesn't really care if the amount of radiation is not too high. An example of a radioactive food that we eat is banana. Banana, believe it or not. Banana is radioactive. In fact, if you put a Geiger counter near a pile of banana, it's going to go off. It's going to go click, 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 because of the potassium-40, which is a radioactive isotope of potassium in the banana. Banana is high in potassium, which is a good thing, but some of the potassium is radioactive. So if you eat a banana, then you are getting a certain amount of small amount of radioactive dosage. Okay, so the radioactive dosage sometimes is measured in so-called BED, that is called banana equivalent dose. This is particularly interesting when you apply it to a radiation leak from a power plant. Say, okay, there is an accident from power plant, so if you live near that power plant, what kind of radiation dosage are we getting? You can measure it in RAMs, of course, and all these, but you can also measure it in BED, which means this is equivalent to eating, for example, 50 bananas. This is equivalent to eating 1,000,000 bananas, so that would be bad. Okay, if the 50 bananas, no problem, right? Okay, now if you eat 365 bananas, which means 1 banana a year, then you expose yourself to this much radiation. Okay, 3.6 millirams. 3.6 millirams. This 0.1 ram, that's 100 millirams a year. That's from background. So eating 1 banana a day for a whole year will give you 3.6 millirams. That's not much. That's not much. Okay, otherwise known as 36 microsievert. Banana is only one type of food that we eat, and generally speaking, the radiation that we get from food every year is about 40 millirams. 40 millirams. It's less than that. It's less than that. But if you combine the radiation from food, from background, and everything, you get a bigger number, which is the amount of radiation that a normal person would expect to go through every year without going through a medical procedure such as CAT scan or X-ray, that sort of thing. Now I have here a radiation chart. The numbers are pretty small, but I'm going to read some of these interesting ones to you, and you can get things in perspective. Okay, there are 2 pages, and here's the first one. Look at these. Look at the color. If the color is like this, that's okay. If the color turns deep blue or red, that's not good, especially with red. Okay, so here is 0.1 microsievert. That's not much. That is what you get by going through an airport security check. You know, these days they let you go through some sort of a scanning device, right? You'll be exposed to 0.1 microsievert. It is about the same as eating a banana. Okay, and then 10 times that, 1.0 microsievert. That is the amount of radiation that you will be getting by using an old-fashioned CRT monitor for a whole year. The CRT monitor does radiate X-rays, but that's not much. You think about it. It's eating about 10 bananas. Okay, that's using CRT for a whole year, so it's not that much. Dental X-ray will give you 5 times as much, 5 microsievert. If you lived in Tokyo right now, okay, 250 kilometers southwest of the Fukushima plant, then this is it's about a half a year after the accident. You'll be getting 7.5 microsievert, which is actually still not much. Okay, still not much. Now you go on higher. A flight from New York to Los Angeles, just one single flight, Okay, one single flight will get you 40 microsievert. That is about 4 times as much as 10 microsievert, which is the background radiation an average person will receive just by walking around in the air. You're getting about 10 microsievert. So this number is not that terrible in Tokyo yet. Now, going higher, 100 microsievert. That's what you get with a chest X-ray. Chest X-ray. Or if you spend 1 hour 3 kilometers away from the Fukushima plant. So 1 hour outside the Fukushima plant is equivalent to getting a chest X-ray. That is 100 microsievert. Okay, and this number 400 microsievert, that is the number that we just saw a minute ago, and that is what you would typically get from food a whole year, 400 microsievert. Okay, now this is 1,000 microsievert, which is 1 millisievert. 1 millisievert. What is that? That is the EPA yearly limit on artificial radiation source exposed to general public. Artificial radiation source, which is not in nature. The permitted amount, according to U.S. government, is about 1,000 microsievert, and that is about 2.5 times as you would get from food. So that's not bad if you can keep it that way. Here is the second page of that chart. Okay, I have so the average dose of annual background radiation is 2,400 sievert for each person, and if you add that to food or whatever, this number here, 3.6 millisievert or 360 millirem per year, that is typically what a person can expect to get from all sources, unless you go to the hospital. CT or whatever, that's another matter. If you're just living normally, that is the kind of radiation you expect to get exposed to. That's a very safe, very small number. Okay? That is 360 millirem or 3.6 millisievert. But if you stand 1 hour outside the Chernobyl nuclear power plant in the year 2010, we're talking about 21 years after the incident, and when everything is already being encased in behind a concrete casing, you're still getting about 600 millirem. So it is more than what we get in background radiation, even though that's still not terrible. Why do I say it's still not terrible? Because the average CT scan, a single CT scan, which is actually a series of multiple X-rays, will get you 10,000 well, actually, it's 10,000 microsievert or 10 millisievert. That is about 1 rem. Okay, so roughly speaking, just about 1/3 of rem to half a rem. That's what we can expect without doing anything special. That's what we expect every year. But a CT scan itself, just a single event, can give you 2 to 3 times as much. So that tells us the CT scan, despite its benefit, does have its side effect, and that is it exposes a person to relatively high amount of radiation. So don't do that unless you really have to. That's the number that you see here. Okay, but smoking is not good. Smoking 1.5 packs a day for a whole year will give you 3.6 times the amount of getting a CT scan. 36,000 microsievert or 36 millisievert. Okay, now one CT scan gets you 10,000 microsievert, but if you go to 100,000, which is 100 millisievert, or 10 rem, if you expose yourself to 10 rems of radiation during a short period of time, okay, concentrated period of time, not over many years, that is a number that will significantly increase your long-term chance of getting cancer. Okay, long-term chance of getting cancer. So it's just like getting 10 CT scans in the same day or something. That is not good, because your chance of getting cancer will be significantly higher, statistically significant. And you go higher and higher, and then at 10 million, 30 million. All these are in microsievert, by the way. All these numbers are millisievert. People can die. 10 minutes exposure to the Chernobyl reactor core after it meltdown. That's going to give you 50 million sieverts. And then, you know what that means? You're going to die if that happens. Indeed, many heroic workers who went in shortly after the meltdown, they have to do something to contain the radiation. Many of them actually died, either shortly thereafter or a few years thereafter, and because they have to build a concrete encasement to bury the rest of the radioactive element, a radioactive core that's still highly radioactive. So that was just very tragic. So again, roughly speaking, every person is expected to get about half of RAM, one third to half of RAM. That's not much. If you go significantly higher than that, you get 10 RAMs in a short period of time, instead of one half to one third to half a RAM in a year. That will increase your cancer risk.